Algebra 2 Honor students, hello and welcome to Unit 8, Day 5. Today, we will eventually get into solving some fourth degree polynomials. Before we do that, I think it would benefit us to do another cubic polynomial. The reason I want to do another cubic is just to make sure we get some more practice using the new synthetic division chart and make sure we feel comfortable using that to find all of the roots. So if here's our cubic polynomial, 4x cubed minus 12x squared minus x plus 3 equals 0. I still want to walk through the same process for setting ourselves up to find all the roots, including Descartes' rule of signs. So for Descartes' rule of signs, if I start looking at the sign changes here, we get plus, minus, minus, plus for f of x, the original polynomial. So I see two sign changes there, one at the beginning, one at the end. And then for f of negative x, we're going to change those odd exponents. So it's negative, negative for x squared, that stays, x to the first switches to positive, and then positive at the end for one sign change. Okay, so when I make my chart for positive, negative, complex cases, hopefully you find that Descartes is going a little bit easier the more and more you use it. First case would be 2, 1, 0. At a max, you'll have two positive roots, one negative root, and then no complex. But then the other possible case would be, since I can decrease the positive column by 2, 0, 1, 2 is another possibility. Now that we've set up Descartes' rule of signs, so we know kind of a little bit about the nature of the roots, the rational root theorem would help us determine what roots I should be testing. So the first thing you'll do is take the factors of 3, the last coefficient. So we'll do plus or minus 1 and 3. And then divide by the factors of the first coefficient, which are the factors of 4. Plus or minus 1, 2, and 4 are the things that would multiply to 4. So if I divide that out and list out all the possible combinations, we would get plus or minus, take those and divide by 1 first, so that's 1 and 3. Then take those numbers, divide by 2 to get 1/2 and 3/2. And then finally take those numbers, divide by 4 to get 1/4 and then 3/4. Okay. So we have a list of 6 potential roots that we could be testing. And hopefully using some of the rules and other theorems like upper bounds, lower bounds, root location, we'll find a root faster than that. But let's go ahead and start our synthetic division, and let's use that new chart format to set ourselves up for success here. So I'm going to make a column on the left called x, and that's where I'm going to start testing some roots. At the top of your chart, we're going to put a 0 there. And whenever you test 0 as synthetic division, you just get the coefficients from up at the top in that polynomial. 4, negative 12, negative 1, and then 3. Remember that the last number, that remainder, corresponds with f of x, the y value on the function. Okay, so you want to kind of block off that row, because every time I go to test root, I'm going to refer back to that row of coefficients. I usually start with 1 as a default. You can start with whatever you want. If you're like, my favorite number is 3/2, then go for it. Try it and see if it works. Okay, I'm going to start with 1 though. I'm going to bring down the 4. You always bring down that first number no matter what. And remember, you just have to do a little bit more math in your head to make this happen. 4 times 1 is 4. And then plus negative 12 is negative 8. Negative 8 times 1 is negative 8. Plus negative 1 is negative 9. Negative 9 times 1 is negative 9. And negative 9 plus 3 is negative 6. Now, you might get to the end of the process and then start thinking, you know what? I know this isn't going to be a root. So do I have to keep going? And in my opinion, the answer is absolutely yes. There's reasons why you want to keep going. One being exactly what's happening right here. What we should notice is that we're going from a positive remainder or a positive y value to a negative y value. So when you see that sign change happen in the last column, that's that root location theorem at work. It's saying we're going from 0, 3 to 1, negative 6. How do I do that? Well, I'm going to have to cross the x-axis. So it means that there's a root somewhere between 0 and 1. If I look at my list, you actually have a couple of possibilities. It could be 1/2, it could be 1/4, or it could be 3/4. Out of those 3 options, 1/2 seems like it might be the easiest to test. But if it doesn't work, have no fear. Maybe try 1/4 or 3/4 next. So when I test 1/2, I'm going to bring down the 4. Half of 4 is 2, plus negative 12 is negative 10. Half of negative 10 is negative 5, plus negative 1 is negative 6. Just make sure you're always going up to that top row. Half of -6 is -3, plus 3 is 0. So we got kind of lucky here that in the end, the value of 1/2, which was my next guess, did wind up working. We got a root. And once you find a root, you get to stop. You're done with the synthetic division chart. You now take these 3 coefficients, just like we've been doing all along, and you turn it into a quadratic and set that equal to 0. 4x squared minus 10x minus 6. So from here, because there's a GCF of 2 that you can factor out, I'm actually just going to divide both sides by 2 to reduce the coefficients a little bit. 2x squared minus 5x minus 3 equals 0. Now, from here, you can either factor, if it's factorable, use quad formula. I probably wouldn't complete the square just because I don't love the odd b term and the lead coefficient. But I'll tell you it is factorable. So for those of you that are quick at using factoring with the lead coefficient, if I have 2x and x to get 2x squared, the way I want to pair up the 3 and the 1 is if I put -3 here and I put +1 there, I know the outside is -6x plus the inside of 1x gives me the -5x in the middle. So then I get the other 2 roots of x equals 3, and then x equals -1/2. And I now have my list of roots. My roots are, going back to 1/2 was one of the roots, right? So we get -1/2, +1/2, and 3. And the cool thing is let's say I had found 3 in my synthetic division first, because you wanted to check all the whole numbers first. Well, then if I found 3, the other roots that the quadratic would have given me are ±1/2. So you will automatically get the other 2 roots if you find any of these first, okay? All right, so what does that look like if I were to make a sketch? Well, let's see. I know we have a root at -1/2, and then at +1/2, and then a root at 3, something like this. And the last thing that you might want to think about just quickly is the y-intercept is 3. Because if you plug in 0 for those x's, you would get a y-int up here at 3 somewhere. So we know that the end behavior is that the tail on the left will go down, the tail on the right will go up. So you're going to get a graph that looks something like that. And I would say that's relatively accurate to what I hope we're about to see when I go to y equals and I type in the original 4x cubed, because checking on the calculator is never a bad idea, even though you won't have one on your test. Minus x plus 3. I'm going to hit zoom 6 just to make sure I have a good window. Hopefully I'm going to cross at -1/2. There we are, +1/2, and then 3. Now, of course, maybe this is a little steeper in certain sections than what I've sketched, but it's just a rough sketch at the end of the day. Okay, if I decrease my y min down to, let's say, -20, I might see the bottom end of this curve. And the cool thing is that even though we can do a lot of this algebraically right now, the study of calculus would help you determine where maybe some of those max and min points occur without using the calculator. So pretty cool stuff that you're going to build upon this in pre-calc and then calculus. Okay. Last thing we're going to do today is what the title of the lesson is. Let's solve a 4th degree polynomial. All right. So let's get a 4th degree polynomial that we can solve. The one that we're going to look at is 4x to the 4th minus 4x cubed minus 25x squared plus x plus 6 equals 0. Okay. So the process is not going to be that much different. Descartes' rule of signs, rational root theorem, synthetic division, all pretty much look the same, even if it's a 4th degree polynomial. But in the end, once I find a root in synthetic division, we know we don't have a quadratic yet. So we'll talk about what we're going to do at that stage in the game. So let's talk about Descartes' rule of signs first. Descartes' rule of signs would say, all right, for f of x, we get plus, minus, minus, plus, plus. And I'm doing some of this pretty quickly now that we've seen Descartes' rule of signs a bunch of times. F of -x, change the odd exponent terms only. So x to the 4th stays, x cubed changes, x squared stays, x to the 1st changes, constant stays. We get 2 sign changes there. Okay, notice I'm making my PNC chart just a little bit longer because we will have a few different possible cases for how the roots could turn out. Could be 2, 2, 0. For the first case, we have 4 roots. So if we have 2 positives and 2 negatives, there would be no complex. But since each of these columns are able to be reduced by 2, that's why we have a couple of other additional cases to consider. It could be 2, 0, 2. It could be 0, 2, 2, right? So either decrease the negatives or decrease the positives by 2. Or how about both at once, 0, 0, 4. I'll give you a little hint. It's not going to be that. I mean, although it's a possibility that we're listing, if all 4 roots were complex, you'd be very mad at me because you'd be testing all your rational roots in your list, and none of them would work. So the rational root list, we're going to take the factors of 6 plus or minus 1, 2, 3, and 6, and divide by the factors of the first coefficient, which is 4 plus or minus 1, 2, and 4. Develop our total list of possible rational roots, which would include take everything, divide by 1 first. That's 1, 2, 3, 6. Then take everything and divide by 2. You get 1/2. 2 halves is 1. 3 halves is new. 6 halves is 3. That's in the list. Then we got to take everything, divide by 4. So you get 1/4. 2/4, which is a half. 3/4, that's a new root. 6/4 is 3 halves, already in the list. So it is kind of a lengthy list for rational roots here. So as we're going through the process, still keep thinking about looking for those sign changes, looking for upper bounds and lower bounds. Those are all things that are going to help along the way in the process. Okay, let's set up our synthetic division chart to start finding all the roots. So we've got x over here. We know that we start with 0 as our initial test point, and testing 0 gives you the coefficients 4, -4, -25, 1, and 6. So I think that the chart is a nice way to organize yourself, but at that, make sure that you're equally spacing out your coefficients. Sometimes I see students like if you're, I don't know, let's say your 1 and 6 were too close. I realize there's that separation there, but sometimes students think that's 16, right? So you just want to be, I think, a little bit careful about how we set up the chart there. Okay, let's start testing and see what happens. I don't know, should we start with 1 again? See if 1 works. I usually start with 1 as a default. Okay, so I'm going to bring down the 4. 4 times 1 is 4, plus -4 is 0. 0 times 1 is 0, plus -25 is -25. -25 times 1 is -25, plus 1 is -24. -24 times 1 is -24, plus 6 is -18. So 1 is not a root. Is 1 an upper bound? Positive, positive? No, it's not all positives. It's not an upper bound, but you're going to see this come up a lot now. When you see that sign change here, it means there is a root in between 0 and 1. It could be 1/2, 1/4, or 3/4. Lots of options there. So let's start testing some of those. Let's see if like 1/2 works. All right, bring down the 4. Half of 4 is 2, plus -4 is -2. Half of -2 is -1, plus -25 is -26. Half of -26 is -13, plus 1 is -12. Half of -12 is -6, plus 6 is 0. So we found that 1/2 is, in fact, a root. Okay, so keep in mind what we're left with is a cubic polynomial. This is x cubed, this is x squared, this is x, this is your constant. So since we can't solve that in a traditional factoring sense yet, you now are going to shrink the equation and use those new coefficients. This step is called depressing the equation, if I haven't used that term yet. Depressing the equation means we're shrinking it down from a 4th degree to a 3rd degree that we have here, and now we're going to test in that 3rd degree. So I'm going to just make a new chart here where I copy these coefficients, 4, -2, -26, and then the last one now is going to be -12. So we're going to continue with a new chart, but this chart is that of a cubic polynomial, such that when I find a root in this polynomial, I'll shrink it down to a quadratic. That's the whole goal. Since I already found a positive root, by the way, I might at this point, just by default, switch over to testing negative roots. If you wanted to keep going with positive, there are 2 positive roots. The only thing you have to be careful about, though, is when we say 2 positive, it doesn't guarantee that they're both rational and positive. I mean, 1/2 is definitely rational, but the other root could be like 1 plus radical 5. That would count as positive, but it wouldn't be in this list, of course. So don't be afraid if you test all the other positives and none of them work. It may be in the end that it's an irrational positive. We're not sure. All right, let's test -1. I'm going to switch over to negative, see what happens. Bring down the 4. 4 times -1 is -4, plus -2 is -6. -6 times -1 is 6, plus -26 is -20. And then you get +20. 20 plus -12 is 8. Well, unfortunately, -1 is not a root, but I hope you're jumping out of your seat and saying, wait, there's a sign change again. So now you're going to go to your list and say, well, maybe I'll test like -1/2 or -1/4 or -3/4, one of those options. You know, and I hate to rule out the others, but I just feel like -1/2 is probably easiest to start by testing. And then if you want to try one of the other fractions because it doesn't work, then you'll go ahead and do that. All right, bring down the 4. -1/2 times 4 is -2, plus -2 is -4. -1/2 times -4 is +2, plus -26 is -24. And then -1/2 times -24 is +12, plus that -12 is in fact 0. We've done it. Okay. So we've now shrunk this down to a quadratic equation, 4x squared minus 4x minus 24. And because there's a really nice GCF of 4, I would divide that out to get x squared minus x minus 6 equals 0. That is a little bit easier now to factor. It's x minus 3 and x plus 2. So with the remaining factors, you get x equals 3 and x equals -2 as additional roots. So it turns out they were nice rational values, but they could have turned out to be irrational in the end. Just kind of keep that in mind. Your total list of roots, you don't have to list them in order, but sometimes it's nice to, would be -2, -1/2, +1/2, and then 3. Right? I got these two roots from the quadratic, and then we found -1/2 and +1/2 using our synthetic division. So just really quick, if I wanted to make a sketch, we would have -2, -1/2, +1/2, and then 3. And we know that the tails are both going to point up because x to the 4th coefficient is positive. So you're going to get your classic W graph for my x to the 4th polynomial. Okay. So that's the only new thing today, really. I mean, I know this is probably a long video for only this one new piece of making sure that we remember, and we've actually seen this before, but in chart format, shrink it down to a cubic, keep testing until you get to a quadratic that you can solve. Much, much more to come with this unit. Let me know if you have any questions about solving 4th degrees next time I see you.